Okay, hello everybody. Welcome to the final session for this course. So we've got two topics for this morning. First of all, we're going to look at the OpenMP memory model, and then we're going to move on and look at some of the more recently added features in OpenMP. Okay, so let's start with the memory model. So a bit of motivation here. So why do we need a memory model? What's all this about? Okay. So on modern computers, code is rarely executed in the same order as it's specified in the source code. And reason for that is that compilers and processors and memory systems are able to reorder a lot of operations in order to achieve maximum performance. So, as long as the program produces the correct results, then the compiler and the hardware is free to reorganize computations, reorder them to maximize performance. So that's what I mean by it. So, and that kind of statement is clear that what that means for a sequential program. So for an individual thread, what we say is that when we, if you think of an individual thread on its own or a sequential program, they exhibit as if serial semantics. Okay, so that means that regardless of any of this reordering, the correctness of the program is preserved. So you can't tell from the results of your program that any of this is happening. And so, what our assumptions of program are based on the memory model like this. We have an assumption about what's going to happen, that our source code is going to be executed correctly, and none of this reordering it matters for correctness. When we come to multi-threaded execution, though, things get a bit more complicated, because we now have the possibility that a second thread is able to observe the effects of reordering in another thread, because the values of variables may change in a different order than what you might expect. So think of a really simple example like this. So we've got two threads. So thread 1 is going to set x equal to 1 and then y equal to 1. And in the meantime, thread 2 is going to read y and store it somewhere, and then read x and store that somewhere. So if there's no reordering, then we can guarantee something about what thread 2 says. Okay, if no reordering happens, then if thread 2 sees y equals 1, then we can guarantee that the following read of x is also going to return the value 1, because the write of x happened before the write of y. So if we read y first, then we should have a guarantee that x has already been written. However, if the code in thread 1 gets reordered, then that assumption no longer holds. And in principle, the statements x equals 1 and y equals 1 have no dependencies between them. So there's no reason for the correctness with respect to what thread 1 computes. There's no reason why the compiler or the hardware should not reorder those statements, okay, if it sees fit. It's not going to affect the computation as perceived by thread 1, but it may affect how thread 2 observes what thread 1 has done. Okay, so as far as OpenMP is concerned, so OpenMP supports what's called a relaxed consistency shared memory model. So what that means is that individual threads can maintain a temporary view of shared memory, so a temporary view of what the values are in shared variables, which is not consistent with that of other threads. Okay, so threads don't always have a consistent view of what's in shared memory, and these temporary views are only made consistent with each other at certain places in the program. And there's an operation in OpenMP which enforces consistency, which is called the flush operation. Okay. So most of what I'm talking about here is the older OpenMP memory model. It was significantly extended as in version 5. I'll say a little bit about what those extensions consist of. But the basic idea has not changed. This is still true. Okay, so what is this flush operation? Okay, it defines a sequence point. Okay, so a point in the program at which a thread is guaranteed to see a consistent view of memory. Okay. And in particular, it makes some guarantees. It enforces that all previous reads and writes by this thread have completed and are now visible to other threads. And it also guarantees that no subsequent reads and writes, so nothing that's going to happen in the future, as far as the program is concerned, have actually occurred yet. So this is what's, if you're familiar with the terminology, this is what's usually called a fence or a memory fence in other APIs. So OpenMP's terminology is a little bit different from the sort of classical literature and other terminology in this respect. Okay. So yeah, so the OpenMP memory model has evolved a bit. So this is actually, if you look at the current specs, this operation is now called a strong flush in the latest specifications, and there are versions with weaker semantics that make different guarantees about reads and writes and so on. But I'm not going to go into that here. So at first sight, this might worry you. You might say, well, why didn't I ever have to, I've never cared about this when I've been writing OpenMP programs. What's the problem? And the reason that you never have to care, or almost never have to care, is that this flush operation is implied whenever we do OpenMP synchronizations. Okay. So for example, at entry and exit of parallel regions, there's a flush. Whenever we have an implicit or explicit barrier, there's a flush. Exit entry to critical regions. Whenever a lock is set or unset. All these synchronization points in the OpenMP program also are sequence points where the memory of the view, when the view of the memory is made consistent. Okay. Chen asks, if we like, can you do a no flush synchronization? The answer is no. Okay. You can't suppress that. Okay. And the reason is that you really, really want this. Okay. It makes correctness of programs extremely difficult to reason about if synchronization points don't also imply flushes. Okay. But just to emphasize also, it doesn't happen at every OpenMP construct. So for example, in particular, the ones that don't synchronize. So example, entry to work sharing regions. So the start of an OpenMP parallel loop, for example, or entry and exit of master regions. There's no synchronization. There's no actual inter-thread synchronization at those points. And there's also no implied flush there either. So as long as we rely solely on OpenMP's provided mechanisms to do inter-thread synchronization, everything's fine. Okay, you never have to worry about these kind of issues at all. You never need to use a flush directive. You never need to care. The problems come is if you decide to try to use regular variables, plain old variables, to implement your own synchronization mechanisms between threads. Okay. And then if you decide to do that, well, hopefully I'm going to convince you that you should never do that, okay? That this is just scary and dangerous and very difficult to get right. Okay. But the point is here, if you did decide, if you were thinking about using just the values in plain old variables to create your own inter-thread synchronization, then that's the point at which you have, that's the situation where you have to care about the memory model. Okay. So here's an example of something you might be, something at some point the kind of thing you might be tempted to implement. Okay, because OpenMP doesn't really have good support for point-to-point or pairwise thread synchronization. So you might be tempted to write something like this. So thread 0 is going to compute some value and store it in a variable A, and then it's going to set a shared flag to indicate that the computation of A has been done. In the meantime, thread 1 spins, okay, and does nothing until the flag has been set, and then it reads the value of A. Okay, and this is supposed to guarantee that thread 1, when thread 1 reads A, the write of A on thread 0 has already happened. Okay, so this looks really plausible. Okay, it looks like that should work, but it doesn't. Okay, and the reason is because of this relaxed memory model. Okay, so lots of things can go wrong here. So the the compiler and all the hardware may reorder these writes, okay, because there's no, as far as the serial semantics of thread 0 is concerned, there's no dependency between these two statements. So it's perfectly happy for the compiler to reorder this thing. Other things can go wrong as well. Okay, so the compiler might decide to generate code on thread 1 where flag is held in a register. Okay. In which case it never reads the value from main memory ever again, and it'll just get stuck in an infinite loop. Okay, so I'm going to try and convince you never to use it, but just so as you're aware, OpenMP does have a flush directive which specifies an explicit flush operation. Okay, and Chen is asking, where do you put the flush to make it work? Okay, I'm going to show you how to do that. Okay, but first of all, let's need to understand what the rules are. Okay, so the way the memory model specification is written, it says that in order for a write of a variable on one thread to be guaranteed visible and valid on a second thread, the following operations must occur in the following order in time. Okay, so those 4 operations are: thread A writes the variable, then thread A executes a flush operation, then thread B executes the flush operation, and finally thread B reads the variable. So if we can guarantee that those 4 things happen in that order, then we are guaranteed that whatever thread B reads will in fact be what thread A wrote. And the important thing the tricky thing here is the second and third one. We have to make sure that the flushes occur in the right order. And that's partly what makes this hard. Okay. So this is, well, this is at least a first attempt at how to do this, okay, with a flush directive. And there's more of them than you might think. Okay, so let's have a look at these, look at individual. Okay, so what are these different flushes trying to achieve? Okay, well, the first one on thread 0 here, that ensures the correct ordering of A and writes to A and flag. Okay, that makes sure that these 2 writes can't get reordered. The second one here is really to make sure that that flag really gets written to memory. Okay, is to prevent, is to make sure that flag isn't just stored in a register indefinitely and before it goes out of scope. So it's really to make sure that this write to memory actually happens. The first and second ones here are on the right hand side in thread 1. These are making sure that flag is actually read from memory. Okay, so again, preventing registerization. And kind of the surprising one is that you need another one here to make sure that the flushes happen in the right order. Because otherwise, there's a situation where you can arrive at this point and the flushes have happened in the opposite order to what's required by the ordering on the previous slide. So nasty, difficult. Okay. Yeah. So I hope I'm going to convince you not to do this kind of thing. Using flush correctly is really difficult. It's prone to subtle bugs. It's extremely hard to test whether your code is correct, and because it might execute correctly on one platform or one compiler, but not on another. Okay, and this is the sort of bug that can be triggered by changing the optimization level on the compiler. The reason why it can change from one hardware platform to another is that different types of processor support different memory models at the hardware level. Okay, so instruction set architectures, so like x86 or ARM instruction sets, have their own memory model, which is basically telling you what happens at what's guaranteed at the hardware level. Okay, so so this is kind of anything that's happening below the compiler, if you like. So what's going on at machine code and hardware level. Okay, and different instruction set architectures like x86 and ARM, for example, have different rules. Okay? So x86 has what's called a much stronger memory model than ARM does. So the ARM one is quite a relaxed model, so closer to what OpenMP has. whereas x86 is quite a lot stronger. So you could be in the situation where you write your code and you're running on an x86 platform and nothing ever goes wrong. But what's happening there is that the bug is never triggered because the hardware is making some stronger guarantees than what OpenMP actually requires. But you could be in a situation where you have code that works on x86, and then you port it to an ARM system, and it doesn't work. Okay. I'm aware of a case where this happened with one of the MPI libraries. So there was one of the MPI implementations had a say it wasn't OpenMP, but it was it was basically the same thing. It was one of these synchronized low-level synchronization bugs in there, and it was never detected because it was basically always run on x86 platforms, and then when it was ported to an ARM platform, it exposed the bug. So it's very difficult. Okay, so I kind of encourage you not to do this kind of thing. Okay. So just as a quick aside, and you'll see why I'm talking about this now, is that there are, as well as the regular atomic directive in OpenMP, which protects updates to memory locations, you can also enforce atomic behavior for operations other than updates. Okay, so you can do atomic reads. Okay, so in this case, atomic read is protecting the thing on the right that's been read on the right hand side here. So that's protecting the memory location of X from concurrent access by other threads. You can do atomic writes, where it's protecting the X on the left hand side here. And you can also have this double statement atomic capture operation. So this is where you want to record the memory, the value of X. You record the old value of X and then update it, all in one atomic operation. And Chen asks, do atomics force the operation into memory? They enforce the operation, but only on the thing that's being protected. Okay, so atomics don't by default imply a flush. Okay, they enforce consistency, but only on the memory location that the atomic refers to, but not on other memory locations. Okay, now there's a way you can change that, which I'll come to in a minute. Okay, so you can make you can force atomics to do full strong flushes. Okay, because strictly speaking here, in the version that I had before, was still incorrect. Okay, so this is still not correct OpenMP, and the reason for that is that there is actually a race condition on flag. Okay, and OpenMP specification says you're not allowed any race conditions. So it's probably harmless, but technically it's not correct. So really, to make this one correct, you would need to do atomic writes and atomic reads for flag. Okay, and you need to do a little bit of reorganization of the code on on this side to make it work, because you can't put atomic directives on reads in the wild conditions. So you have to basically introduce a private variable and have explicit reads into it. Now, there is a better way of doing this, and that is by forcing the atomics to also imply the relevant flushes as well. Okay, so you can actually write this in a sort of vaguely sensible way by using atomics with the SECCST, which stands for a sequential consistency memory order clause on atomic directive, which implies all the right flushes for you. So there kind of is a vaguely sensible way to make this pattern work in OpenMP, but nevertheless, it's it's really not something that you should try and do without a very careful understanding of what you're doing and whether it's correct or not. Okay, does anybody have any other questions about that? Okay. So my final topic is to look at some of the newer features that have been added to OpenMP, which you may or may not have come across, and may or may not ever care about, or ever want to use. But hopefully, some of them might be of some interest. Okay, so it's quite a long list of things here. It's certainly not an exhaustive list, and it's not an in-depth. I'm not going to go into a huge amount of depth in any of these topics. Okay, as I say, there's now an awful lot of stuff in the OpenMP specification, and it's just difficult to keep up with what's in there or how it's supposed to work. As a caveat, I should say that not all compilers may necessarily support all of these features. It depends on the version of OpenMP that the compiler supports. You can, in principle, query that or look at the documentation for the particular compiler version and see what they usually make statements like, okay, this version of the compiler supports version OpenMP 5.2 except for the following features or things like that. So it can be difficult to, so some of the more recently added stuff may not be as portable across different compilers as you might like. Okay. So I should say that the the OpenMP specification itself is a very tough read. It's like most language specifications. It's written in a very careful way, but that also means that it's there are lots of lots of definitions, and everything is defined in terms of something else. So you have to go down, if you want to understand what something means, you have to go down a whole tree of glossary entries and try and unravel it all. So it's really not that easy to understand. So these days, what's probably more helpful is that there is an extensive, as well as the actual specification, there is an extensive examples document, which has example code and actually runnable example code for a lot of the features. And that's often a much better resource for trying to find out how things work. So I recommend, if you're doing OpenMP development, if you haven't ever looked at that, getting hold of a copy from the OpenMP website is well worthwhile. Okay, so in no particular order, let's start with user-defined reductions. Okay. So the reduction clause in OpenMP, so the built-in version, is limited to basic data types or arrays of basic data types and a restricted list of operators that work on them. Thankfully, it does now include min and max for C and C++, which it didn't used to. They are just defined as the usual macro that everybody implements to do min and max. So that's one relief. Okay. However, if you want to do reductions on non-basic data types, so structures or objects, for example, then you can define your own reduction operators. So there's a declare reduction directive which does the definition, and then once you've defined them, you can then use them in a reduction clause in the normal sort of way. Okay, so the declare reduction directive looks like this. Okay, there's a reduction identifier. Okay, so that's the name that you're going to use as the operator in the reduction clause. It then takes a type name list. Okay, so a list of types for which this reduction operation is valid. And then a combiner expression. So this is a code fragment which expresses how two different objects or things of this type should be combined together in order to form the reduction operation. And then optionally, you can also specify an identity expression as well. Okay. So that's that will determine how the private copies of the reduction variable will be initialized. Okay, so I think I've probably covered this slide, but I should have gone on to already. Yeah, so reduction identifier gives a name to the operator. You can overload that for different types. Yeah, names, list of types, type name list of types which applies, the combiner expression, how to combine values, and the identify specifies the identity value. Okay, so let's have a look at an example. So this would be, okay, suppose I've got vectors in the C++ STL, okay, and I want to define an operator which just merges which merges or concatenates vectors together, okay. So if I've got, every thread is going to have a vector, and what I want to produce at the end is a vector that contains all the pieces merged together. Using this declare reduction, okay, so I've got to give it a name. It's called merge. The list of types that it's going to apply. Okay, so I'm just going to keep it simple. It's going to apply to stud vectors specialized on int. And then I have the combiner expression. Okay, and in order to help you in order to be able to sensibly write the combiner expression, there are these two predefined variables. Okay, so OMP out is going to refer to the private copy that holds we're going to pass in, and is also going to hold the combined values as an output. And OMP in is the other private copy that we're going to combine with. Okay. So my combiner expression for this would look like this. Okay, so I'm going to insert at the end of OMP out, the end of the OMP out vector, all the elements of OMP in between its beginning and its end. Okay, so you have to know what the signature of the insert method for vectors is here. So it says basically this is where to put it, and this is the start of the things you're going to add, and this is the first element of the things you're going to add, and this is the last element of the things you're going to add. Okay. So what this does is basically, this little expression will take OMP in and OMP out vectors, and it'll produce in OMP out the concatenation of the two. Okay, so once I've done that, then I can just use merge in a reduction clause on parallel regions or parallel loops in the normal sort of way. Okay, so a couple of other extensions to reduction operations that have been added. One problem that can happen is that inside a parallel region, and you want to force a reduction operation to happen at a particular point inside a parallel region. And previously, there wasn't really a way to do that. You had to sort of fake up a loop that forced the reduction at the end of the loop, or something like that. Okay, but now there's this thing called a scope construct now, which basically does nothing on its own, but you can have a reduction clause that on it. And what that does is it forces the reduction to happen at the end of the scope clause. At the end of the scope construct. Okay, so you can have a parallel region here, okay, and a shared variable A, and okay, so set an initial value and correctly synchronize that in a single region. And then I can have this scope reduction construct here. So I can increment A from different threads and then force the reduction to happen at the end of this construct. And then what I read here is in A here is the result of the reduction. also possible now to do reductions on private variables inside a parallel region. So previously, and this is only coming in version 6, so you're probably not going to see this in implementations quite yet. But so this is again to try and to overcome some limitations of doing reductions, because currently, or at least before version 6, you can only do reductions. I can only do a reduction on a work sharing loop inside a parallel region if the reduction variable is shared, and that's basically a little bit restrictive. So this can be cases where you actually want to do reductions on private variables, but you have to think a bit carefully about what does that mean. Okay, so what really happens here is that it actually creates it basically creates a hidden shared variable, which will be initialized, in this case for additions, will be initialized, where with private copies initialized to 0. Okay, it'll then make the reduction into that hidden shared copy and then use that to increment all the private copies of A. Okay, so in this case, I've got private variable A, which has some initial value, and in principle, it does not need to have the same value on every thread. And then I can have a loop which does a reduction operation, okay, so which increments this variable A, and the result that you get after the end of the loop here. So this A here still refers to the private copy, but every private copy will have been updated with the sum of all these additions. So you have to kind of think a little bit carefully about what it means, but it turns out that there are these sensible semantics for doing reductions on private variables, and that's what this does. So Raymond asks, new features, does it mean there had to be at least one implementation? The specification process encourages demonstration implementations, but doesn't mandate them. Try very hard to not to put stuff in the standard that's unimplementable. Okay, and a lot of the people who work on the specification are in fact the compiler implementers. So there is a reasonable process to try and ensure that what goes into the standard is implementable. Anytime soon is a little bit tricky. Okay, there is always some delay. There's always a certain amount of time between the standard being published and compilers catching up with it and implementing it. And that depends on, some compilers have got more people working on their OpenMP implementation than others and are more aggressive about it, but it's usually on the order of 1 or 2 years between the specification being published and those features getting reasonably wide coverage in compilers. Okay, so Marcus says, in the previous example, what happens if A was not initialized to 0? Yeah, that's fine. Okay. So this is not the initial. This is not giving an initial value to the reduction, the private reduction copies. Okay. So inside the parallel loop, what's going to happen is you're going to get different separate private copies, okay, different private copies of A, which will be initialized to 0, okay, and then you'll get the sum of those formed at the end, and then whatever that sum is will then be added in to all the individual original private copies, okay. So if so, what comes out at the end is kind of what you'd naturally hope for, okay? It's the original value of A, whatever that happened to be, plus all the increments that were made inside that loop. Yeah, so it does. It took me a while to try and get my head around what the semantics were for reductions on private variables, but I think I've convinced myself that it makes sense. Okay. So as well as reductions, you can also do prefix scans in OpenMP. Okay, so this is to compute. When you're if you're doing a reduction, so you don't just want the final result, but you want all the partial. You want all the partial results as you go along as well, all the partial sums as you go along as well. And so you can do that. So the syntax is a little bit complicated because you basically have to specify where the result is going to go, and also whether it's inclusive or exclusive. So inclusive means that the kth value includes the value from the kth iteration, or exclusive where the kth value only has the values up to k-1. So you do is you modify the reduction clause with this in-scan keyword here. Okay, so you still need the operator and the variable. Okay, and then when you want to every time you update, every update that's made to X, then you store the result in an array that's going to hold the result of the scan, and you do that with this, and that store is indicated to be the scan by this scan directive here. Okay, and then this could be either inclusive or exclusive here. Okay. Next one we're going to talk about is construct cancellation. So this is a clean way to signal early termination of an OpenMP construct. So the way this works is that inside an OpenMP construct, like a parallel region or a work sharing loop, then it's possible for one thread to raise a signal, and then at some point later, where that's well defined what those points might be, other threads will observe that signal and they'll stop whatever they're executing at that point and jump straight to the end of the construct. Okay. So this is useful for operations like parallel searches, for example, where you're interested in I'll show you an example in a minute, where you're basically interested in you just want to search for, and you're just interested in the first item that matches something, and as soon as you found something, you want to stop all the threads executing and carry on doing something else. Okay, so the way this works is that there are two directives involved here. There's a cancel. Okay, so that's what raises the signal. Okay, so the cancel directive, you have to specify what construct it is that you want to jump to the end of. Okay, because that could be ambiguous. You could be, you could have a parallel region which contains a work sharing loop. So, this allows you to say, okay, I want to jump to the end of the loop or jump to the end of the enclosing parallel region. Okay. And this can be conditional on some expression. Okay, so you can put a condition on in here as well. So if expression evaluates to true, then that will raise the signal. And the allowable constructs are parallel and sections and work sharing loops and task group. Okay, so those are the possible places that possible constructs where you can jump to the end of. We also have a cancellation point directive, and this is just a place that that enforces thread to check to see whether a signal has been raised. Okay. So the check also happens implicitly at other places. Okay, so in particular at the cancel construct itself. Also, even if the if expression evaluates to false, it still forces the encountering thread to check to see if some other threads raise the signal. And also things, so synchronization points like barriers as well. Okay, so whenever you come to a barrier, then threads will also check to see if the signal's been raised. So just to sort of sketch a piece of code, which would, might say, this is, example where you want to just stop as soon as one thread's found something. Okay, so I've got a loop where every iteration does some test and returns true or false, and you want to stop the loop as soon as the first true value is encountered. Okay. So you could do it like this. Okay, so we want Eureka to be a private variable, and then I can use the cancel construct. So I say cancel the parallel region if Eureka is true. Okay, so the first iteration where Eureka is true, that signal will be raised, and then because the cancel construct itself acts as a cancellation point. And so other threads, as soon as they've finished this this function call, they will, regardless of what value they returned, they will check to see whether the signal's been raised, and if it has, they will skip to the end of the parallel region. So this kind of pattern is, it's possible to implement it without these constructs, but it's kind of messy. So this gives you quite a nice, neat way of implementing this sort of pattern. Do I have any details on how this is implemented? No, that's down to the implementation and how well it performs. No, actually, I don't. I'm not aware of any either. So I think you'd have to do your own I think you'd have to, if you're interested in that, I think you'd probably have to do your own investigations. I wouldn't have too many concerns about performance here, because really what you're really always doing is, is setting up a shared variable internally, which threads can read and write to. So the check is really just doing some atomic read on some internal shared variable, I would guess. Okay? So I would expect the implementation to be reasonably efficient. And of course, it has to implement a jump to the end of the parallel region, but I would not have thought that this would be too bad in terms of, I wouldn't have thought this would incur too many overheads. But that's just my best guess, okay? And of course, it depends on individual implementations, what they do. Okay, so at this point, I think this would be a good point to have a short break. Let's give ourselves until 10 past, okay, and I'll carry on then. Okay, so the question from Chen about support for vector processors. I'm not aware of anything beyond what I'm about to talk about now, okay, beyond the existing support for SIMD directives. Okay. So this is something that's maybe slightly an odd thing to be included in OpenMP, because ostensibly it's nothing, although it's to do with parallelism at some level, it's not to do with threaded parallelism really. But the motivation here is that a lot of compilers support their own directives to aid vectorization of loops, because the compiler can find it difficult to generate SIMD code without some additional information supplied by the programmer about things like the independence of loop iterations and the alignment of data structures as well as another thing that the compiler may not necessarily know and is important in order to be able to generate efficient vector code. So OpenMP, as of OpenMP 4, has provided a standardized set, which have been, as far as I know, pretty widely adopted by most compilers. So most compilers do support the OpenMP version as well as their own proprietary version of SIMD directives. So the main way this works is the SIMD directive to indicate that a loop, so this is a directive that applies to immediately following do or for loop, to indicate that it should be SIMDized. And so this will execute the iterations of the following loop in SIMD chunks. So this directive of itself does not divide the loop across threads. So you have to use it if you want thread parallelism as well as vector parallelism, then you have to combine two directives. You have to do OMP for SIMD or OMP do SIMD. Okay. So the way the terminology is dealt with in OpenMP is that a SIMD chunk is a set of iterations executed concurrently by SIMD lanes. Okay. And there are some various clauses which control data environment, how loop is partitioned. So things like safe len, okay, so that puts a limit on the number of iterations in a SIMD chunk. If it's not safe to, it's not safe to let the compiler make its own choices. Linear lists variables with a linear relationship to the iteration space. I'll come back and talk about that in more detail later on, because that's also applicable in contexts which are that's also applicable for parallel loops nowadays, as well as for SIMD loops. It's aligned, so you can specify the byte alignments of a list of variables. So you can guarantee some alignments, and then things like last private reduction and collapse clauses have their usual meanings that you would expect from parallel loops. There's also a declare SIMD directive where you can generate SIMDized versions of functions. Okay, So the functions have to be, there are certain restrictions on there. They basically have to be, pure functions that, there's restrictions on the type signature that you can have there. Okay, but you can, it will allow the compiler to generate vectorized versions of functions. So if you have functions which are called inside loops which you want to vectorize, then that can help in that case. Okay, yeah, and as I said, you can combine this with the OpenMP loop constructs, so that will parallelize the loop across the threads and vectorize it as well. Okay. Next one is the affinity environment. Okay, so most systems now we have NUMA, non-uniform memory access domains, of SMT, so simultaneous multi-threading, hyper-threading, virtual cores, hardware threads, whatever you like to call them. There's way too many different names for the same thing. And also have complicated cache hierarchies where certain sets of cores may be sharing certain level 3 caches, for example. And so as mentioned before, so the AMD Rome processors in ARCHER2, you've got a node contains 2 sockets. Each socket is a chip with 64 cores. Every set of 16 cores is a separate belongs to a separate NUMA domain. Every set of 4 cores is attached to a shared L3 cache, and every core supports 2 hardware threads. So there's this the hardware has a really complicated hierarchical organization, and there are cases where you may care about how your threads are bound and running on the different bits of that hardware hierarchy. So support that, and as also mentioned before, on a lot of supercomputer setups, HPC system setups, thread and process binding and placement is controlled by some combination of the batch system and potentially the OpenMP runtime as well. So there's a bit of sort of interplay and mix and match going on there, which is different for different batch systems, and also depends on how your batch system has been set up as well. So it's all a little bit messy. The support that OpenMP gives you are a couple of things which are done through environment variables. So there's the OMP procbind environment variable, which already existed way back when, which you can still just specify true or false, which says, please bind my threads to cores, but I'm not going to tell you which ones, or false, which means don't worry, just let the threads float around and migrate between different cores. Okay. So you can now provide a list, okay, as well, with values which are include master, close, or spread, which specify how to bind parallel region at different nesting levels. Okay, so you can say, and I'll talk a little bit about how these work. Okay, so basically, master says put them in the same place as the parent thread. As we're thinking about nesting here. Close says put them on next to each other, but not in the same place, but as close as you can in the hardware hierarchy. Or spread says spread them out across the hardware as much as possible. And then there's also this OMP places environment variable. So that allows you to say, okay, what which entities do these concepts, master, close, and spread, apply to? Okay. So you can specify abstract names, so you can specify threads, so that means hardware threads, okay. Cores, that means physical cores, and sockets, which probably means pseudodomains. So, so this is a problem with this, where, this terminology was introduced as a certain, when hardware looked a certain way and hardware has evolved. And so it's the same problem with batch systems as well, okay? If you look at what, if you look at the sort of Slurm documentation as well, for example, you'll see that it also has concepts about hardware hierarchies, but they don't exactly match what you see in modern processors either. So there is this there can potentially be some ambiguity about what these terms actually refer to, and that will be implementation dependent. You can also specify an explicit ordered list of places. So this gives you the ability to say, I want to select a certain subset of cores where I want my threads to run. Okay. But exactly how the numbering works is implementation defined. Okay. So you have to read the compiler documentation to figure out what it actually means. Okay. So this is all really designed for nested parallel regions, but doesn't really work so well for hybrid MPI and OpenMP code, okay? Because that really needs some combination of this and the batch scheduler, as I was kind of indicated, to get everything correct. Okay. Because there isn't really a sensible way, for example, of you can't do this sort of explicit ordered list of places and have a different list for every, what you'd want would be a different list for every MPI process, and that there isn't really a way to do that. Okay, so here's an example. Okay, so suppose I have two levels of nesting. So I've got to doubling those nested parallel regions. Okay, and I'm going to have by setting the number of threads here, I'm going to have 4 threads at the outer region and then 2 at each of the inner regions. That's actually not quite right. That's not what's in my diagram. Okay, I think I really mean 4, 4 here. Okay, so I'd imagine I've got hardware. So my hardware has 8 cores and has 4 hardware threads per core. So this is some imaginary chip which probably doesn't really exist, but just for purposes of an illustration. Okay. So I can set OMP places equals threads. So that means that the entities that I'm talking about with proc bind are hardware threads. And then I want the binding to be spread at the outer level and close at the inner level. Okay, and that would achieve something like this. So my initial master thread would run on hardware thread 0 on core 0, so that's here, and then I would get 4 threads at each of the next top level parallel region, and I ask for spread, so they'll be spread as far apart as possible in the across the cores and hardware threads, and then close in this case would mean that I would actually get so you have to really think about you have to consult the details of there's in the specification it says exactly how this works, but in this case I would get my inner threads. I would get 2 of them on this core and 2 of them on this core for the ones that were spawned by this master thread. So you can do, you have some control like this over how your threads get bound. So next topic is the masked construct. So I'm afraid I'm not very, I'm still stuck talking about master threads, which I really shouldn't, because that terminology has been, and the construct themselves have actually been deprecated, and it still works. Okay, it's for backwards compatibility with older codes, but master has now been renamed masked. Okay. And the terminology has been changed as well. Okay, so inside a parallel region, we're supposed to not talk about the master thread. We're supposed to talk about the primary thread, and the thread that executes outside of parallel regions is the initial thread. But I'm afraid that I've been slow to adapt this new terminology, because, and partly because if I use it, nobody knows what I'm talking about. But that's the way the specification is these days. But the semantics have been extended, so that's part of the reason for renaming it to masked. Is it's now possible to select threads other than thread 0 to execute the block of code, and potentially more than one thread to execute the block of code. And the way this works is, again, it makes sense when you think about it for a while, but at first sight, it's a little bit odd. Okay, it says if the argument to the filter clause matches the number of the encountering thread, then that thread will execute the block. Okay, so the argument to the filter clause can be different on different threads. And if it matches the thread ID, then that causes that thread to execute the block. Otherwise, it will ignore it. Okay. So the original master construct is equivalent to, well, masked does the same thing, but that's also equivalent to masked with a filter clause with an argument of 0. Okay. So if all threads pass 0 as the argument to the filter clause, that means only thread 0 will match that and execute it. But if more than one thread matches, they will all execute the block. So it's possible to do slightly odd things like this, which is, say, okay, suppose I have an execute a block of code only on the even number of threads. That it's possible to do that. Okay, so you could have this variable which I've called include me here. Okay, so if my thread number is even, then I could set include me to be equal to my thread number. Otherwise, it's -1, and then have a masked construct and pass include me as the argument to the filter clause. So that will match only this variable only matches the thread ID on even numbers of threads. So the even numbered threads would execute this block of code. So you can do weird stuff like that. Okay, so I mentioned the linear clause briefly. We're talking about SIMD directives, and so just a little bit more detail here. This is to deal with what's called induction variables. Okay, so induction variables are variables in a loop variable in a loop which is incremented by a constant every iteration. Okay, and that that pattern will normally prevent the straightforward parallelization of loops, because that forms that increment of that variable forms a dependency between the loop iterations. It's usually fairly trivial to refactor that. So instead of incrementing a variable, you just write an expression for it that depends. That's a linear function of the. You just write the linear function of the loop iterator explicitly. But so the refactoring you need to do to make it to allow parallelization is usually pretty trivial, but it can be unwanted or tedious if there's a lot of cases, and means anything you need to do to refactor code to implement OpenMP is generally a bad thing. You don't want to be forced to. You really like just to be able to add directives and not to rewrite code in principle. But you can handle these things by specifying them in a linear clause. Okay. So in this case, the induction variable is j here. Okay, so that's incremented once every iteration. Okay, and in this case it's not the same as I, because I is incremented by 2 every time. Okay, so we can handle this and safely parallelize this loop by specifying it in a linear clause and specifying the increment. So again, a bit like the SIMD directives, in the past, compilers have seen fit to provide support through directives for controlling loop transformations. So things like loop unrolling, loop tiling, loop interchange, loop reversal, and again, every compiler had their own syntax for these kind of directives. So a bit like SIMD, again, this is kind of, outside. I would say it's outside the original conceived scope of OpenMP, but it turns out that for these things, for these compiler directives, OpenMP is a convenient place to standardize them. Instead of the alternative would have been to set up a completely new specification body to deal with SIMD directives or loop transformation directives with all the administrative overhead that cause. So it seemed to make sense to import those standardized directives in as make them part of OpenMP, even though they're really not quite relevant to multi-threaded parallelism, if you like. Okay, so OpenMP now supports portable mechanism for these transformations and also combinations of them as well. Okay, and there's quite a lot of them here, and how you combine them and so on. There's quite a lot that you can potentially do with this, and I'm not going to go into the full details here. Just give you a couple of examples of things that you can do. So this is by no means a complete treatment at all. So, for example, suppose you've got suppose I have a loop of length 4, and I just want to force the compiler always to fully unroll it. And so I could say hash pragma. I should be an OMP in there. Sorry, hash pragma OMP unroll full, and that will do the job. Okay, so that will force the compiler to fully unroll this loop. Or you can do, you can also combine parallelism and loop transformations as well. So you can do OMP parallel do, tile, and then give it the tile sizes. So it'll basically say, okay, I'll take this nested loop, I'll decompose it into blocks of 5 × 16. Okay, so 5i iterations and 16j iterations, and then distribute those blocks across the different threads. So you can do things like that with these directives. Something else that's been added is synchronization hints. So you can give a hint about the expected use of synchronization constructs to help the implementation select the best option for them. So there's different ways that you can implement locks, and the most efficient implementation depends on the use case. So, for example, in particular, if we expect lots of threads to be always accessing these synchronization constructs, so it's very likely that when threads encounter a synchronization construct, they're going to have to wait for another thread to release the lock or so on. So the optimal implementation for that case is different for the optimal implementation if we expect that to happen very rarely. So if we expect most of the time that when threads encounter a lock or a critical section, the lock's going to be free and available. So we can give a hint as to what we expect to happen in our application. So that's one hint we can give. The other one is probably less useful. I'm not really aware of implementations that take great advantage of this. Is speculative or non-speculative. So this is basically if your hardware has transactional memory support to say whether that might be useful or not. The way it works is that critical and atomic constructs take a hint clause. Okay, so if you have an atomic update, you can say, and you expect you expect collisions between different threads for the same memory location to be very uncommon, then you can say OMP sync hint uncontended, and then that will allow the implementation to select the implementation of the atomic that best matches that use case. For locks, it's basically done with at the lock initialization time. So you can basically call OMP. There are corresponding functions. You can call OMP init lock with hint instead of the standard OMP init lock, and then pass that a hint as well. So for locks, yes, it's done at the point of lock initialization. Next one is schedule clauses for parallel loops. So older versions of OpenMP actually mandated that loop chunks are assigned to threads in their logical order. Okay, so for example, for a dynamic schedule, the specification said that the case chunk must always be assigned to a thread before the case plus one chunk. So the assignment had to happen in the logical order for the loop. But as of version 5, this restriction's been relaxed. The chunks can be assigned in any order. And so this can improve data affinity and reduce some synchronization overheads. You can implement some sort of basically a kind of work stealing implementation. So where different threads start at different points of the iteration space, and then if they run out of things to do, they'll basically help out. Threads that finish early will help out other threads that are more heavily loaded. So that makes for more potentially more efficient implementation. You also get better. You can also get better cache reuse, better data affinity from that kind of method instead. You can control this though, okay? So you can enable or disable it, okay? So there are monotonic and there's a monotonic and non-monotonic keyword which goes in front of the schedule kind on the schedule clause. So the default behavior these days, okay, is monotonic for static and non-monotonic otherwise, but you can change it if you want to. Okay, and a last topic is meta directives. So this is syntax that supports runtime choice of OpenMP directives without having to explicitly write conditional code. Okay, so if you want, if you have a piece of code and you want, depending on, could be runtime, could be compile time. But if you want to generate conditional code, so you want, a version of a loop with one OpenMP directive and another version with another OpenMP directive, a different OpenMP directive, and you want to the ability to select that without explicitly having, an if test and 2 copies of the code, then that's what the meta directives are supposed to do. So they are quite powerful. You can do tests based on program variables. Okay, so flags, whatever that you set inside the program, or you can test on other things. You can say, okay, test on the type of the offloading device. Okay, so depending, what sort of GPU have I got attached, you can do make different choices depending on the model of GPU, or also on the instruction set architecture of the CPU. So depending on, for example, what SIMD instructions are available. So does my CPU support AVX512 or not, for example? So you can make choices on those kind of things as well. It also allows you to create code variants and select and make a runtime selection about which of those is used. So you can have, you can create multiple instances of functions and then pick one at runtime. So again, so I'm really giving a very light treatment of this. There's quite a lot in there that you can potentially do. But so here's a fairly simple example though. Suppose I have a parallel loop which sometimes is going to be executed lots of times. Sometimes the load balance is good and other times it isn't. Okay, so you could basically say, okay, depending on a user specified condition, so I'm going to use a program variable called unval here. Okay, a flag called unval. If unval is true, then it will select the directive for OMP4 with a guided schedule. And this says the syntax is a little bit messy, but if unval evaluates to false, then it'll go to the otherwise branch here, and it'll use a for directive with a static schedule. So say that's a relatively simple example. You can do more complicated stuff than this. But again, so the philosophy here is it allows you to do that kind of thing without having to do code rewrites, without having to do code refactoring, and particularly without having to duplicate code in branches of if tests. Okay, that's the end of my slides. So does anybody have any questions about either that last session or anything else that we've covered in the course? Oh, thank you very much. Notice that last session is a new one and there's a few typos in it, so I need to go and fix those. Great, thank you very much. Glad it's been useful. Okay, so if there's no other questions, then we'll finish 10 minutes early. Thank you very much for your attention and for your questions.